Welcome guys to another session on dynamic programming. Topic today is DPV 6.29 Exon Chaining, and this is an interesting problem that describes how DNA sequences are made up of two kinds of um, sequences. Things that we care about are called exons, and there's some what is called as a junk DNA, and that is called intron. And I've provided a link here for a nice intro on what exons and introns are. So you can go check that out. But for the sake of dynamic programming, all we need to know is that there are these sequences called exons, and we need to link these exons together to see what is the longest exon that we can find inside this the sequence that is provided to us. So um, so that is essentially the problem. And another piece that is given to us is that you can think of each of these exon as a triplet, which is it has, let's just think of one of these. Let's just take an example of one of these. So if you look at this sequence, it'll have a starting, which is the left side, the right side where it ends, and a weight assigned to this, how important this sequence is. So think of some other algorithm, maybe the local sequence alignment or some other algorithm that has given us a start and point, left, right, which they call it, and a weight. So let's say you are given a bunch of these elements, and now you are asked to find the longest non-overlapping, right? The important thing is that you have to find the ones that are not overlapping, and you can chain them. For example, you cannot chain these two, but you can chain this one with this one, right? And then you cannot chain these with this one, but you can chain this with that one. And so if you can chain these with non-overlapping sequences and find the longest possible sequence in this case. And we have to show how to do this efficiently, and that is the objective of this problem. So this problem has been, I believe, defined in um, this website here from University of Illinois, and you can look at this lecture 7 here, um, and I am just trying to illustrate this algorithm that has been provided for exon chaining here. So the important thing here in this algorithm, which kind of resembles, if you look at it, the hotel problem at the very beginning of the chapter 6. Um, so the way to approach this is think of, first of all, this graph has to be constructed. And the way to construct this graph is that first, for every location, there is a node, right? There is a vertex. Um, and then you just create a link, a forward going link from left to right, but assign zero weight to it, right? And that's the simple thing. And now you take each of these triple sequences that you were given, and let's say this one goes from 1 to 5. You just make from 1 to 5, you make a link, and then you add a weight of 5 on it, right? So likewise from here 4 to 8 with a weight of 6. So you put from 4 to 8 with a weight of 6. You put an edge like that. So basically you translate all these triplets of the subsequences that you have found, and then you map them into this graph. So at the end of that exercise, you have this graph that is given to you. And now the algorithm can apply dynamic programming to this graph to figure out what the longest sequence of chained exons will be. So let's look at that next. So the algorithm is that first you initialize these all these locations with 0. So for each node you have a slot, and you initialize all these slots with a 0. And then you will go through each one of them, and then you see on each location, you see if there is an arrow for one of those subsequences that ends on that location. You figure out what the the beginning point of that location is, and then whatever its current maximum um, weight is, or SJ value is. And then you add the, the weight of the arrow that is pointing towards you. So this is one possibility. The other is SI minus 1. So the max of both of those would be put into this. If there is no arrow ending on you, then you just take the previous one. Now, don't if you don't follow this, don't worry too much, because as we run through the examples, it will start to make sense, because this is very much like the hotel problems that we solved at the very beginning of the chapter. So let's just look into the example, and now it'll start to make sense what we're saying. So let's just initialize this whole array for one for every node, and then initialize them with all zeros, right? And so let's just run through the very first one. There is nothing before zero, it remains zero. Now when you come to the first node, you see that there is no subsequence ending here, so you can just copy the previous one, it remains zero. You come to the third node. Now at the third node there is a sequence ending here, so you have to take a max, and the max is 0 plus 3 or I minus 1, which is 0. So it's a max of 3 or 0, which becomes 3. Okay, so that's the key here. Look at this, that if a subsequence ends here, you will see this arrow pointing here. At that point, you take the previous value here, which is in this matrix is 0. So you make a 0 plus 3, one path, or just I minus 1, this one. Okay, and so it's a 3 and 0 max, which becomes 3. Next is just a copy, because there's no sequence ending here, I minus 1, you put it here, it becomes 3. Now in this case, there is an arrow ending here, so you look at this one, 0 plus 5 or a 3. So max of 5 or 3 becomes a 5. Next we go to this, copy the previous value, becomes 5, copy the previous value, becomes 5. Now here, you can come from here, 3 plus 6, 9, or you can copy the previous. So 9 or 5, you get a 9. Then nothing ending here, so you can copy the previous, which is 9. Now the next one, it's either 9 plus 1, 10, or copy the previous 9. We take a 10. Okay, next one, we just copy it. Next one, again, this is 5 plus 10, 15, or 10. So 15 or 10, max is 15. Copy the previous 15, copy the previous 15. Now here another sequence is ending here. So you take 10 plus 7, 17, or 15. Then answer becomes 17. This is just copy the left. Here it's a sequence is ending here. So you take 5 plus 12, 17, or 17 becomes 17. Okay. And then finally, this one is 17 plus 4, either 21, or copy the previous 17. So the answer is 21. So that's the final value, and that is the longest sequence. When you reach the S, the last, the nth value here, then that becomes your answer, right? Because at that point, you know what is the longest weight sequence in this exon chaining that you can find. And this would, then you can backtrack it to see how you arrived at 21, and you can see which sequences you used, and you can find them by backtracking from the largest value and see where those came from. So this is essentially the algorithm. Now it is order n time, because you only had to run through each sequence once, and you either uh, you know, it did not check all the previous values, right? You didn't check all the previous values, because you could see that either an arrow was ending there, or you take the previous. So there's only two computations, either this one or this one. So you didn't have to go all the elements before that and see which path came through to this and which was the best and so on, right? You didn't have to do that. So the trick here was using the I minus 1 or the max path ending here, which was, whatever this Sj plus weight or Si minus 1. That is the algorithm. So that's it for exon chaining, guys. And like I said earlier, this is very similar to the hotel problem that we did earlier in the beginning of the chapter. And this seems like towards the very end is a repetition of very similar problem on exon chaining. Now, this is a very interesting topic because it deals with the genetic sequencing, and it's a fairly important topic. So hopefully you enjoyed it. And if you did enjoy it, and you have been with me for this long, we are almost to the end of this chapter, then do give me a thumbs up, or subscribe to my channel, keep coming back, because this whole sequence that is available on my YouTube channel is something that you don't have to just watch once. If you keep watching it, you'll begin to see patterns in the dynamic programming. Like in this one, we saw that this was kind of like the hotel problem. You will see some of the problems are like chain matrix multiply problem kind of solutions, and and so on. I mean, there's backpack problem. So you see that the themes are repeating over and over, and that's how, by practicing these problems and listening to them again and again, you will begin to recognize these patterns, and then apply them quickly when you're given a variant of this problem. So that would be my advice, is that keep watching, keep repeating, and as you go through the problems, new problems, you have to kind of break them down into one of these patterns that you have seen before. And that would be my advice for people who are just beginning to program using dynamic programming approaches. And those who have been doing it for a while, it just helps to refresh your memory on how these various algorithms work and how they break it down, and how you had seen a pattern before, but maybe you're not seeing that pattern yet into this new problem. It helps you see that pattern. All of a sudden, you'll say, aha, that's how it works. And all of a sudden, without even looking at what I'm saying, you will recognize that that's the pattern here, and it'll click. And that's it. So thanks a lot for watching this episode, guys. And I hope you had as much fun as I had making it. And until next time, take care and bye bye.